I'm flattered so many people are still here. Actually, an acquaintance of mine told me of a conference where there was only one person in the audience. So he said, okay, let's go to a bar, I'll tell you all about my talk. And then the guy said, oh no, I'm sorry, I'm the next speaker. Yeah. I'm a little bit, it's a pity that sign language interpreters are not here. I think that most of you still here are nerds, probably. And I think that all of you also had this idea, you want to make an experiment, self-referential experiment. How would they respond if you go, I think the sign language interpreters are really good. It would be interesting to see them say that. You know, I wonder if something would happen. Okay, anyway. Okay. So, I wonder if, has any one of you heard my presentation at SICS Open House? Okay, this is new for most of you. Okay, so I will talk a lot about biology. I spent a good deal of the last 10 years actually studying biology. I'm not a biologist. Is there any biologist in here? Okay, great. Oh, there are a few. Oh, I have to be careful. So I assume that most of us are computer savvy. So this is mostly what biology can teach us. But I think there are actually also, if you were biologists, I could sort of change it and say that what can AI and machine learning teach the biologists, because there are definitely points there too. But anyway, this is from the point of view of the computer scientists. And biologists, they often have a presentation of their team in the beginning. And these people deserve a lot of credit. My, Henrik, my closest collaborator, he's a biologist in Lund. He's a fantastic experimentalist. He's an electrophysiologist who actually measures individual neurons and gets the signals. That is something very difficult, and I've been very lucky to have been able to work with him. Daniel, you know, he's the AI specialist, and Lars is the super programmer, and I'm the guy who comes with coffee to the others, you know. Okay, also there are many other people here, many neurophysiologists who I've learned a lot from, and I would like to especially give credit to a person who mentored me very much, Bror Alstermark, who very sadly passed away last year. But he has been a probably you don't know him, but in the biology community, he was an international star. He made some really amazing, had some really amazing experiments showing things about the connection between the cerebellum and the spinal cord. And he was also very interested in mathematics, and this is quite rare for neurophysiologists. Okay, so let's look a little bit at biology, the human brain, or actually the mammalian brain, the däggdjurshjärnan in Swedish, and compare it with silicon of today. And I think we can see something quite interesting. It is a fairly reasonable approximation to say that the human brain contains has approximately 1 petabyte of information. This year, I saw for the first time a commercial 3.5-inch SSD disk with 0.1 petabyte. So 10 of those is approximately the same information content as the human brain. Okay, the human brain consists of about 10 to the 11 neurons, which have a propagation delay of about 1 millisecond, and consumes on the order of 100. That's a peak power of 100 watt. Whereas the NVIDIA GV100 GPU has about 2 times 10 to the 10 transistors. Propagation delay is a bit faster. On the other hand, neurons do a lot of things, so they are approximately on a par, I would say. The memory bandwidth of the human brain is a little bit hard to measure, but you can say quite safely it is very much less than 600 gigabytes per second. If every axon in the brain communicates at the maximum capacity would be something like this, but that would be a very serious case of epilepsy. So it's really much less of that. The PCIe bus, I think, which you can actually buy, is about 16 gigabytes per second, so they are also comparable. So altogether, the hardware of a very high-end PC, desktop today, and the human brain are quite comparable. And the human brain is actually, the basic structure of the human brain and all mammalian brains are approximately similar. So why are computers not even close to solving human problems yet? And by human problems, I don't mean chess or Go. I mean something like a strong AI, a general, or sometimes people prefer to refer to artificial general intelligence. Something that can solve a lot of problems, use knowledge from one problem in another problem, and generally behave in a way which is human-like. Why do we have this difference? When the hardware, I think, say, from this year, approximately from this year, actually, high-end desktops have approximately the same performance, hardware-wise, as humans. Okay, so people have thought about this before, and I would say that we are seeing a lot of discussions which already existed around 1950 with Norbert Wiener, cybernetics, John von Neumann, and many of these guys. And at that time, it turned out that I would say that people didn't know so much about computers. So computers got a lot of attention, and AI and neuroscience or biology started to diverge. But I would say that now, since about year 2000, it's quite clear that these two are converging again. And there are really very interesting features in each field which you can actually use for stepping ahead in the other field. So, but not many people do this because now machine learning and biology are very separate. But I can see in many places these are reconverging. And this is especially interesting in learning, which is a really big thing in biology and neuroscience. And that's what I would like to place some special emphasis on. Okay, so let's have a closer look at the brain. When we talk about the brain, I don't know, some of you maybe were at the computer architecture workshop yesterday. It was very interesting. Someone mentioned actually that the brain is definitely not a computer. Let's see what I think about that later. But people think that the brain, that's a network of neurons. And then if we use sufficiently many neurons and make the network big enough, and we sit there and wait, intelligence will appear. Okay, doesn't sound very reasonable, right? But still, there are really huge projects in the world where people spend lots of money on this. Okay, so I think this is actually a problem. It could lead to another AI winter, and that would be a pity. So I think we should look at the brain. The brain is good, but we should look at it from another perspective. Okay, instead of bottom up, let's look at it top down. So the brain consists of 4 major components. It's the cortex, cerebral cortex, which many people think of as the memory, which is a good idea, I think. There are the basal ganglia, the thalamus, and the brainstem, which is not in this picture. And the thalamus, what the thalamus does and what the basal ganglia do and what the brainstem does, maybe people are not so, there's not so much a consensus. But let me give you a simple view which I think can be quite enlightening. So rather than, this is the picture you see in textbooks, and sometimes photographs look like this, you know, PET scans and things, imaging like this is very popular. There is a much better way of viewing the brain, which is not so popular these days because people used it a lot, say, 60 years ago. It's very tedious and very hard, very difficult to use this, and graduate students don't have so much patience these days, so it's hard to make them do it. But it is something called a fiber dissection. And I think that this is probably the best big picture of the brain I've ever seen. This is from a textbook by Glubegovic and Williams from 1980. It's extremely difficult to find any pictures like this now. The thing that makes this so good is that it shows so much in detail You can see the cortex here. You can see the memory bus, or the called corona radiata. You can see the part of the basal ganglia here, the thalamus here, and the brainstem here. And it's so, you can see the connectivity, it's so beautiful, of course. Lots of things have been removed. But if I draw these pictures here, you can recognize again these names. And let me show a little animation here. Let us unfold these. And here you have a nice block schematic. Okay. Took me a long time to do this, so I like watching it myself. I'll show it to you once more. Okay. So, really nice. Okay, so we can draw this as a block schematic. Now I rotated it 90 degrees. The cerebral cortex here, the basal ganglia here, I drawn arrows through them because they have a lot of learnability, or plasticity, the biologists call it. They change depending on your experiences. Then thalamus here is like a switching station. It does not have very much plasticity. So one thing which is special, I should say, about this connection here is worth saying a little bit more about, because it's exclusively inhibitory. It can, what it does is actually it's bombarding the thalamus with inhibitory signals. So normally, the normal state here is that it inhibits signals. However, depending on the signal here from the cortex, it can relieve these inhibitions so that signals pass through here. So it is actually strictly a control signal for the thalamus. It doesn't pass any data to the cerebral cortex. And all of you have probably heard about the Parkinson's disease. And the problem with what happens in Parkinson's disease is that this is frozen in an inhibitory state, so it becomes very difficult to change this. This is sort of set in some behaviors, and this is a typical symptom of Parkinson's disease, that you want to do something, you can't do it. It's most known for the motor programs. You cannot move the way you like, but it also has cognitive effects. It's actually quite an unpleasant disease, but it's actually malfunctioning of the basal ganglia. Okay, now you may have seen this diagram before somewhere. Actually, I showed it by mistake just recently, but you may have seen it anyway. And maybe you recognize these names here: central control organ, central arithmetic organ, and memory organ. Because there was a gentleman who wrote a report, and section 2 of this had exactly this structure. It's the first draft of a report on the EDVAC. So John von Neumann gets a lot of credit for this, but it was also Eckert and Mauchly who was behind this. It was the first description of the von Neumann architecture, and I can recommend, you can find it on the net. It's really interesting. And it has, von Neumann, he really liked to describe things with biological terms about organs and things like that. And Eckert and Mauchly, they were really irritated. They were electronics engineers. Why mixing this stupid biology in this? But now I actually have an advantage. It makes it easier to explain. So nowadays we use different terminology. We call this central control organ, we call it an instruction decoder, and the thalamus and ALU, and together we call them a CPU. But this is the fundamental function of a von Neumann computer. So what I'm saying is that if we look at the block diagram level, the brain is really a von Neumann computer. I would say it subsumes a von Neumann computer because there are additional connections. I haven't drawn this brainstem here. The brainstem corresponds to, if you are PC guys, you know about the South Bridge. Nowadays it's called the peripheral control hub. It's a piece of hardware you find in any PC which controls the USB devices, peripheral devices, and low-speed things, and take care of the low-level things. And that is the same as a brainstem. It takes care of the heartbeat, of the breathing, and all these vital functions. That's a place where you really don't want to have a stroke, because then it's goodbye directly. The cortex is not as life-critical at all, but it's in the same way as for a PC, it's very important. Okay, so seeing the brain as a computer, and not only a computer, a von Neumann computer, is really very useful for understanding what is happening, and gives you a lot of useful intuition about problems. And we can push this analogy further. I could stand here and rant for a long time. There is a part of the brain which is called the hippocampus. You might have heard about. That's very similar to cache memory. It's actually a cache memory, a write-back type. You write back in the night. This is not controversial in the biological community, in fact. There are lots of experiments, but it has the most complicated circuitry in the whole nervous system. Lots of people are working on it, so it's not so strange if it's a cache memory. It has connections to all kinds of places. The cerebellum, which I didn't talk about before, located in the back of the head, this is very similar to a general-purpose GPU. It's not life-critical. Some people are born without it. It's called cerebellar agenesis. It's actually quite interesting. It makes you slower. Everything you do is slower. You will not be able to do juggling or dancing on a line, but you can live without the cerebellum. Yeah, I also mentioned brainstem. So what is the point I want to arrive at? Well, we know a lot about the brain's hardware. You know, you can look at every big-time neuroscience project. You can look at the flagship project in the EU. You can look at all these projects, and people are obsessed with the hardware. You know, all these hardware projects is doing as many neuronal operations per second as possible. And so the idea is that, okay, we're building this, which has the same computational power as the human brain, but we don't know what it should do, you know. We don't know about the software, okay? The brain is a von Neumann computer. Then, by definition, it has some software. The contents of the cerebral cortex controls our operations. But what are the instructions? What are the programs actually running there? You don't find much discussion about this. But you find people trying to find the neural correlates of consciousness. Consciousness is sort of the most high-level functionality we could imagine. And I think this is like finding what is the transistor correlate of a web browser. Suppose we have suppose we didn't have computers and there's some extraterrestrial accounts there with a computer. And he has a web browser. And okay, we want to understand how the web browser works. Okay, so we manage to open his computer and we break a transistor. Ah, the web browser stops. We found where the web browser is located. You know, that's sort of the level where we are right now at understanding consciousness. It's so many levels different. So we have to start to think about what is the software running on this computer. So, okay, now specifically about learning. So the classical view here, I think you're all, if you look at the literature, is still many of the theory books at least say like this, that supervised learning is not so controversial. It's essentially function approximation. We have some x-y pairs, and we want to, for future x, we want to sort of approximate what y would be in those cases. Unsupervised learning, people are there, maybe not, people are a little bit more vague there, but the classical examples is clustering. Perhaps K-means is the most well-known algorithm. There is also dimensionality reduction. Okay, but now I think that now quite recently, this year or the last 3 years maybe, started coming the idea, a more, I think, general idea of unsupervised learning, which has turned out to produce amazing results together with supervised learning. And you may have seen the term semi-supervised learning and self-supervised learning. And that is actually a function of unsupervised learning is to produce the feature sets for subsequent supervised learning. Often we have lots of data, sensory data, which is not very structured. But in order to apply supervised learning on them, they must be tagged. This is really awkward. So often we don't have so much data which is tagged. And Kalle Åström, he subjects his poor students to horrible experiments. And what you run out of students. So his fallout, we inherited RISE. That's for Arthur. When he had hit his head too many times, he came to us. So Kalle, he has a problem. He cannot get so much data here. Well, what he does first is, of course, to use all these masses of data to extract an embedding, like Word2Vec is a very nice program. I think most of you have heard of it. That's a really nice idea. I think it doesn't have anything to do with neural networks. You should see it as an optimization problem. There are many ways you can do that, but the really nice function, I think, of unsupervised learning is to produce representations on which we can then apply supervised learning. You know, that feature engineering, doing it manually, I think that's nobody wants to do that. It's too hard to do. But if you can use unsupervised learning, that's great. Okay, so now let's map this to the human brain. And I'm a bit speculative, but I wouldn't say this is very controversial. We are born with a biological substrate which has Hebbian synaptic plasticity, which works quite well. We do, however, have very little knowledge beyond that. This is a topic of discussion among psychologists, but I think the main mainstream of psychologists think that we actually bootstrap from a very low level. But we do have the circuitry to do unsupervised learning, and then probably this unsupervised learning creates some kind of embedded representation, some embeddings, on which we then apply supervised learning. Okay, but the thing with humans is it doesn't stop there. You know, we have something about logic and reasoning. I would say logic is a bit tainted now since the 80s. Some kind of principles or rule-based things. We also heard a little bit earlier presentations to do. Something like that which allows us to avoid making experiments. Like you can imagine you have a robot on top of a skyrise building. You can't really do many experiments there because they are fatal. It's better if you actually can use some kind of reasoning that probably the stairs are better without actually having to try it. Okay? Now we go back. And so what this suggests to us is that there should be something more after supervised learning. I don't know really what to call it. If I should call it program learning, where we don't have any data. So when Kalle has run out of his poor grad students, and he's sitting there alone in his lab, what should he do then? You know, so a concrete case: someone for autonomous driving, for instance. For autonomous driving, it's easy to collect lots of data. It's much harder to collect tag data. But then, how much data can you gather having a moose running out in front of the car, or a 3-year-old with a ball? You can't really simulate that. Even if you have graduate students, you don't want to do those experiments, right? So, but a lot of things that we call common sense is somewhere here, and it's not differentiable. We cannot use gradient descent on these problems. But it is there, and so I would say that the big problem, if you have a solution to this and plan to publish it, send it to me first, I'll check it. Because it's the transition here. We shouldn't do like we did in the 80s and sit here and write our rule-based system for trying to find the rules for them. We want to go continuously from the differentiable supervised learning to program learning. We want to develop programs that learn other programs that then learn other programs that then maybe solve the problem. Okay. The psychologist view, I don't have so much time to talk about it, but Kahnemann's book, maybe you've heard, I can warmly recommend it, and Bror Alstermark also very warmly recommended it. And he was a die-hard core neurophysiologist. It was one of the best books he has ever read, and he bought it both in English and in Swedish, which says something. Psychologists talk about system 1 and system 2. So I would say unsupervised learning and supervised learning is very much the lower loop here. The next level is the system 2, and that's what we need really to learn seriously. So the conclusions is the brain subsumes a von Neumann computer, the brain learns programs, and there is a transition from differentiable to non-differentiable learning. And that is something that we really need to know before we can implement anything like strong AI. Okay, questions? Thank you.
Right, great. Thank you, Martin. I have 5 minutes of questions. See, there's someone who was very quick over there.
Hi, thank you for an interesting talk. I was thinking about your complaint that consciousness and trying to infer that from the hardware is difficult, or infeasible perhaps. But we're born with consciousness and we learn everything else.
You know, the problem is that I don't even have the tools to think about consciousness. It could be an emergent property. I really don't know.
Maybe consciousness is the operating system.
Could be, maybe.
Maybe that's the very, very fundamental thing that you need to solve problems, and then you get more sensors and more actuators.
It could be. I don't dare even to philosophy. You know, it's a little bit dangerous for an engineer like me to discuss. I actually discussed it with Daniel Dennett, who wrote a book which is called Consciousness Explained. And this is a case where an engineer should stay skomakare blivit in läst. I don't know what that is in English. But you know, consciousness had been studied for so long by so many expert philosophers. They have a whole tool set, of vocabulary, literature references. It's really a swamp for people like me. So I don't dare. I would say, you know, my guess, far out guess, is that it is maybe some emergent property of the software processes that are running in our brain computers, but it's on a very high level, and we're very far from reaching that level. But it's something there, I believe.
There's someone in the back.
Yeah.
What about inheritance and inherited firmware, low-level stuff? For example, monkeys in captivity are frightened of snakes and so on.
Inheritance?
Yeah.
You mean that children learn from parents or inherit?
I mean, yes, we have some low-level firmware. What do you think about that? How much does that affect what we process?
I think humans don't inherit so much software. I think we inherit the basic principles of learning. Learning programs too. But I don't think we learn very much factual knowledge from genetically. I think there is not that much. I think we have something like, is it 3 billion base pairs? That isn't very much, really. If you're a computer person, you know, one base pair is 2 bits. So we have only 6 gigabits in the DNA. That's not very much.
Okay, I think we need to finish right here. So thank you, Martin, for a great talk.
Thank you.
Thank you.
I hope your head doesn't hurt too much.